Today we're going to talk about composition of linear transformations and matrix multiplication. Let's review some ideas from last time. Say that we have a vector space over a field. We define a basis by a set beta satisfying one of the following two properties. Either beta spans V and beta is a linearly independent set, or we can say that every vector x in our vector space V can be uniquely expressed as a linear combination of vectors from beta. Using this concept, if we have a basis beta, then first we're concerned with the order of the elements. We'll call this an ordered basis. That is, that the element that we call the first element versus the second element will be important to us. Second, since for our basis, we know that every vector x can be written uniquely as a linear combination of elements from beta, we'll consider the scalars a1, a2 through a sub n that appear in such a linear combination. The coordinate vector of x with respect to beta is this vector that just consists of these scalars. Say now that we have two vector spaces, V and W, having bases beta and gamma respectively. Let's say that T is a linear transformation. First, the coordinate vector that we wrote before allows us to define a linear transformation. That is, given a vector x from our vector space V, the vector that we get by just looking at the scalars corresponding to the linear transformation will define a linear transformation itself. Second, let's say that we do have our linear transformation T. Then by simply looking at the scalars that we get from a couple of linear combinations, we can define an m by n matrix. This matrix will denote by A in your screen. The map phi sub beta will be called the standard representation of V with respect to our basis beta. The matrix A, which will denote by square bracket T subscript beta and superscript gamma, is the matrix representation of T in the ordered bases beta and gamma. One big question that we'll be motivated by is, how do we actually compute this matrix, the matrix representation? But more importantly, let's stop and ask, why are we defining the standard representation and this matrix representation? Well, given a vector x in our vector space V, recall that we have a linear combination in terms of the basis elements in beta. We really only need to keep track of the scalars a1, a2 through a sub n. Those scalars form the standard representation phi sub beta. Given a linear transformation T, recall that we have linear combinations by looking at each vector V sub j in the basis beta and expressing that as a linear combination of the vectors W sub I in the basis gamma. Again, we really only need to look at the scalars capital A sub I. These scalars form the matrix representation. Let's consider a rather quick example. Let's say that V and W are both R2, the real plane, and beta and gamma are the standard bases in terms of the vectors you see on your screen. Say now that we have a linear transformation T that sends a vector x, y to the vector T of V, which is ax plus by, cx plus dy. We'll compute the matrix representation from the basis beta to the basis gamma. First, observe that we can look at the images of our basis elements E1 and E2. Then we can express these as linear combination of the same basis elements E1 and E2. By looking at the scalars we have here, namely A, B, C, and D, we can write down our matrix representation. As a proposition, we'll summarize as follows. Our linear transformation, which sends a vector xy to the vector ax plus by, cx plus dy, is equivalent to the 2 by 2 matrix A, B, C, D. That's the concept of our matrix representation. It just keeps track of the scalars. Today we'd like to discuss the composition of linear transformations to explain a little bit more how this is related to matrix multiplication. First, let's remind you, what do we mean by the composition of functions? Let's say that we have two well-defined maps. Let's call them T and U, one going from V to W, the other one going from W to Z. The composition U circle T is that map from V to Z that sends a vector x to the vector U of T of x, which lies in Z. You can see here from the graphic on the screen what's happening. We'll start with our domains on the very left. In this case, it's denoted by capital A. We can then map all the way to the right for our codomains, capital C. The composition here maps from the left to the very right, where you can see here, one of the subtleties is that the notation is a little bit backwards. First you apply F, going from A to B, then you apply G, going from B to C. The composition G circle F, again, notice that the notation here is backwards, goes from A to C. Let's say that we have three vector spaces, V, W, and Z, all defined over a common field F. We'd like to state three fundamental properties. First, let's let script L, V, W denote the collection of all linear transformations T going from V to W. This collection itself, this is the set, is also a vector space. Let's say that T and U are two linear transformations. T goes from V to W, and U goes from W to Z. Not only is the composition U compose T well defined, it's also a linear transformation. Finally, let's say that V, W, and Z have bases beta, gamma, and alpha, respectively. Of course, we can consider the matrix representation of T going from beta to gamma, and the matrix representation of U going from gamma to alpha. We'd like to know how that's connected to the matrix representation of the composition U circle T going from beta to alpha. Well, the statement is that this matrix representation of U compose T is actually the product of the other two matrix representations. Of course, throughout the course of the proof, we'll define what a matrix product is, and we'll go over some examples. For the moment, let's stare at the following diagram to get a better idea of what's happening here. On the left, you'll see our various linear spaced vector spaces, their bases, and also what happens with the standard representations. Here, T maps from V to W, U maps from W to Z. Sitting inside of V is our basis beta, sitting inside of W is our basis gamma, and sitting inside of Z is our basis alpha. The standard representations allow us to take a vector x in V and write the coordinate vector, square bracket x sub beta. We have similar maps for W and for Z. But if we look at the very bottom rows, this should all correspond to multiplication by matrices, namely A and B. As we go through the proof, we'll explain in a bit more detail what's happening with this diagram here. Let's start by showing the first statement, that this script L of VW is a vector space. To do so, we of course have to explain what do we mean by vector addition and scalar multiplication. So we'll begin by explaining the triple you see here on your screen. First, what do we mean by vectors in this sense? Well, the elements of this script L VW are just a collection of linear transformations going from V to W. Vector addition here will be defined in a slightly strange way. Given two linear transformations T1 and T2, we'd like to define what we mean by a new linear transformation T1 square box T2. We'll do so as follows. This linear transformation now needs to be defined by sending one vector to another vector. We'll define it as follows. Given a vector x in our space V, we'll define the sum T1 box T2 as the sum t1 of x plus t2 of x as the sum of vectors in our codomain W. We have a similar definition for scalar multiplication. Given two linear transformations t1 and t2, as well as a scalar c, we'll define the scalar c dot t1 as that linear transformation that sends a vector x in the domain to c times t1 of x in the codomain. I want you to keep in mind here that when we write t1 plus t2, or when we write c times t1, these are rules. Our rule says if we start with the vector x, we can write down a new vector, either t1 of x plus t2 of x, or c times t1 of x. Again, t1 plus t2 is a rule, and c times t1 is another rule. In order to show that our triple, this script L along with our box plus and with our box dot, is a vector space, we must verify that 8 axioms are true. We'll leave the verification of these 8 axioms as an exercise. Now let's show the second statement. That is that the composition is also a linear transformation. The basic idea here is that we need to make sure that our composition preserves linear combinations. To this end, let's take a linear combination from our vector space capital V. We know that since T is a linear transformation, we can apply T to our linear combination X, and we have another linear combination in terms of the vectors VI. Similarly, let's choose a linear combination in our vector space W, and let's apply our linear transformation U. Since Y is a linear combination of vectors, we know that U of Y is another linear combination of vectors. Finally, let's very specifically choose each Wi as equal to T of Vi, so that we see now what happens with the composition. The composition U circle T applied to our linear combination X will once again be a linear combination. Since the composition U circle T preserves linear combinations, we see that this composition is indeed a linear transformation. Finally, we'll show the third statement. That is the statement about how the matrix representation of a composition is just the product of matrices. To begin with, let's try to remind ourselves what are the definitions of these matrix representations. Since gamma here is a basis for W, and recall that beta is a basis for V, remember that we can apply T to each of the basis elements in beta and express that as a linear combination of the basis elements in W. This means that we can find scalars Aij such that you have what you see here on your screen. Similarly, since alpha is a basis for Z and gamma is a basis for W, we can apply U to the basis elements for W and express those as linear combinations of the basis elements for Z. So we can find scalars Bij such that you see what you have here on your screen. By collecting the scalars together, we have our matrix representations for U and for T. These are the two matrices you see here at the bottom of your screen. Now, let's apply our linear transformation U to the very first set of equations. This is how the composition works. Once we do this, then we see that we have a collection of linear combinations where now we've applied the composition U circle T to the basis elements for V and expressed this as a linear combination of the basis elements for Z. By combining equations together, we can see explicit formulas for our coefficients. Here, we'll define the Cij as just the entry in row I, column J of our matrix product. If you will, this is our definition of a matrix product. We'll come back to this in just a couple of moments. This means now that we can actually write our matrix, the matrix representation of U circle T, as a product of matrices. Again, this is how we're defining the product of matrices. as just the formulas that you get by substitution. In particular, we find the formula that we first claimed. Let's try to go through a couple of examples. We've already seen that the product of a 2 by 2 matrix and a two-dimensional vector is another two-dimensional vector. Indeed, if we take the matrix A11, A12, A21, and A22 times a vector xy, we can write this as a two-dimensional vector A11x plus A12y, A21x plus A22y. More generally, we can take the product of an m by n matrix and an n-dimensional vector to find an m-dimensional vector. Again, the formulas that you see here are almost the same as what you see for the 2 by 2 case. The product of two 2 by 2 matrices is another 2 by 2 matrix. Just by using the formulas that we had on the previous slide, again the definitions, that we can write out a very specific case as you see here on the screen. More generally, if B is an P by M matrix and A is an M by N matrix, then the product here should be an P by N matrix. You can see the expressions here in terms of the entries of this matrix B times A. Thanks for watching.